A particle is being lowered on a string. We want to know the tension in the string if, in part A, it is being lowered at a constant speed of 4 meters per second. Constant speed is the important thing here. Newton's first law tells us that if the speed is constant, then the forces must be in equilibrium. In other words, there is no resultant force acting on this particle. The forces acting on the particle are its weight, 5 times gravity, and the tension in the string. And we know here that they must be equal, so T is equal to 5G, and taking G equal to 9.8, this gives us 49 newtons. Now we have the object accelerating downwards at 0.2 meters per second squared. The same two forces still apply, the 5G downwards and the tension upwards. However, now the object is accelerating in this direction at 0.2 meters per second squared. So there is now a resultant force. Remember, in F equals ma, the F is always the resultant force. And the resultant force acting on this object is 5G minus T. The weight acting downwards, take away the tension acting upwards. This is going to be equal to the mass times the acceleration. So 5G take away T is equal to 1. 5 times 9.8 is 49. And this gives us that T is 48 newtons. Now in part C, the particle is still being lowered, but its rate of descent is slowing at 0.5 meters per second squared. In other words, the acceleration is now upwards. Since the particle is being lowered, but the rate of descent is slowing, the acceleration must be upwards. The same two forces still act, the weight and the tension, but the acceleration is now upwards, so the resultant force must be upwards. The resultant force is T take away 5G, and that will be equal to the mass times the acceleration. So T take away 49 is equal to 2.5, and so T is going to be equal to 51.5 newtons.